This webinar is entitled Alarm Limits versus Trending, and my ultimate goal is to show the negative side of alarm limits and, of course, the positive side of trending to try and show what would be the best tool in terms of interpreting most of your oil analysis data. Now, to begin this webinar, I thought it was worth taking a step backwards in time and looking at the history of oil analysis. So here's a quick overview of how oil analysis got started. The railroad industry was one of the first ones to actively engage in oil analysis as a preventive maintenance strategy. About a decade after this happened, the United States Naval Bureau of Weapons was looking into it. And within a few years, you started to see trucking companies use it. After the initial successes, the very first independent commercial oil analysis lab was opened, and the rest, as we say, is history. Now, why I point out this timeline is just to highlight what it was like back then. All of those early adopters had a few things in common. They were all very large fleets with a very limited number of different OEMs, model configurations, things like this. Almost without fail, the only sample that was taken at drain. It was always taken from the same location and under very similar operating conditions. Because if it was a trucking company or a railroad, they would run the same routes, they would operate the same way, so even seasonal variances would be accounted for. The other thing, though, is there were very few customers and there were very few labs. Therefore, there was a strong relationship between the labs and the customer. So if the results came back a bit weird, the customer usually could phone up the lab and they'd have a discussion about it. If, for whatever reason, a failure was missed, again, the customer could work with the lab to reestablish some alarm limits and make them better. In today's world, if this was to exist, we would refer to this as big data. This is what we use today to try and make sense of a whole bunch of data. And that's something that they were able to do 60 years ago when oil analysis was really kicking off. They could figure out what normal looked like, and they could see what was the trend towards the abnormal variances or triggers, and set the alarm limits to ensure that the warning came soon enough, but not too soon and not too late. Now, the nice thing is like I said, because they had these large fleets always operating up and down the same roads, the same rails, they could account for any seasonal variations or operational variations as well, and make sure that whatever noise occurred in their data didn't trigger any alarms. So this is how good it was. And this is, like, again, oil analysis at its infancy. And the thing is that this established a reputation for oil analysis that has carried forward to today, but actually is no longer that valid. A good example would be to show you what oil analysis today looks like. So your average commercial oil analysis lab deals with all sizes of fleets, right down to a single one-off application. We have virtually an unlimited variety of OEMs and models. We now take multiple samples per drain interval. So we're not just sampling the end of drain sample, we take what we call mid-interval samples. We have less control that the samples will be taken from the same location under the same conditions every single time. And given how many people have adopted oil analysis, there's many, many more times customers than there are labs. So there's a much weaker relationship between the customers and their labs, to the end that most labs are unaware of any efforts the customer may be making to extend drain intervals or extend mean time between failures or any of the other common metrics that you might look at. And where this kind of gets funny is that to this day, we will still receive samples and they'll be marked something like Gearbox 101A and no other information. They can't even tell us what kind of oil it is, what brand of oil it is, what viscosity it is. We don't have a sump volume. We don't have any make model information to go with it, nothing. And why I point this out is even though these types of samples still hit the lab, the most common thing people are going for is to ask a question like, what's an acceptable level of, whatever it might be, a wear metal, a contaminant, a degradation property. And that is a very, very difficult question to answer when so little is working in our favor anymore. So what I'd like to do in the beginning part of this presentation is walk us through where some of these static alarm limits come from. Now, basically, there are four main sources. You can get them straight from the OEM. You can get some from your lubricant suppliers. If you're lucky, you might have industry-specific limits. These might come from user groups or other organizing bodies. But ultimately, most people do rely on the commercial labs to provide some set of limits. Now, as I go through those first four, what I'm basically going to do is absolutely tear them apart and point out how lousy they are. Most of them don't work well on most samples most of the time. Ultimately, what you would like to work towards, if you felt static alarm limits were the thing to do, they would be set by the end user and they'd be in line with any goals they have. Now, I'm not going to show how to do that. I'm going to then transition over to trending, but I'm going to go through these first four and explain to you why they're so bad. So every one of these is a real example. I credited some of them. The ones that I pick on the most, I don't tend to credit because be disparaging towards the person who supplied it. But let's start with OEM limits. So here's an honest-to-goodness published OEM limit. There's a major typo in this table that I guess was never caught, and I've reproduced the typo just so you can see how basically little these tables might be used, because somebody should have caught this and fixed it. But let's look at just the title of this table. The first word in the title says suggested. So it says suggested. So is this the limit, or is it only a suggested limit? How do you interpret the word suggested? Then the second word says safe. So am I to understand if I stay under these limits, I'm always safe? Does that mean if I go over the limits, it's unsafe? Like, what do you mean by safe? So when we say words like suggested, safe, it really is a loose interpretation of what we're going to look at these numbers. Now, the whole time I've been talking, perhaps somebody has picked up on what the typo is, but looking throughout this list, at the very bottom, 10 parts per million. If you told me how big the system was, I could find a way of representing what 10 parts per million looks like, how much tangibly that would actually be in terms of bits of material. But if you look at the top of this table, 15 parts per million natural gas engine, I don't know how I can show you that. So I'm just pointing out kind of the silliness of this table, that somebody didn't catch on to that particular line in the table. But here's the text that came with the table. And it's actually pretty reasonable. Now, this is not my all capitalization. That's exactly how it was published. And so it says, these charts are for general use only and do not indicate definite limits of wear metals for any specific make or model. So when you read that, immediately you wonder, well, just where do I use these? Because clearly they're not meant for anything in particular. So does that mean they're good generally, or they're no good at all? The second sentence says, wear patterns are best established after evaluation of 3 samples taken at the same oil change intervals. That is a really good point, and I'm going to come back to that one later. But the last sentence says, make, model, application, age, makeup oil added, time of use, or recent repairs. I mean, I might as well have continued that list and said the number of wheels, the color of the vehicle, and all kinds of other stuff. It says, can cause the values to vary greatly from those shown. So ultimately, they put this disclaimer next to this table that outright said, this table's no good. They're admitting it. So why do OEMs publish limits like these? Well, they're really only there to highlight major issues, and most of them are surrounding some type of warranty dealings, whether it's a warranty claim or just ensuring the proper service is done during the warranty period. But generally speaking, the OEM's level of interest is centered around making sure they can get through the warranty period. Now, the other little tidbit I'll throw in there is that generally speaking, it's implied that all these limits apply to the end of drain samples only. They don't really give you any clue as to what it might look like during service, just at end of oil drain. Now here's another quick example of an OEM supplied limit. This one says water contamination of engine oils in concentrations as little as 500 ppm can seriously affect the oil's filterability and the function of the oil's additive package. Well, that sounds fairly serious. But then the second sentence says the detection of water in concentrations above 0.3%. Now it's funny, they switched units of measurement here. So I've given it to you, it's 3,000 ppm. It says warrants immediate corrective action and an oil change. Well, that's kind of interesting because they provided us with two different limits. They said at 500, it could be a problem, and at 3,000, we should definitely do something. But that just begs the question, what do you do in between? Like, that's a big gap. So is this caution and critical, or what are we talking about here? So this is not a great limit in the essence that if we set 500 as our alarm limit, we might go into alarm because there's a potential for a problem, but doesn't necessarily mean we need to do an immediate action. But if we set the second limit for saying, okay, you must do an immediate action, well, there's 2,500 ppm in there where it could cause serious harm. So if you see what I'm saying with this, it's not very good. So looking at OEM limits, generally speaking, we don't find a whole lot of good information presented here. So where some people look is the lubricant supplier. After all, we're measuring oil, so wouldn't the people who make the oil know the product the best? Well, they might, and they might publish tables such as this one. I mean, if you scan down the list of criteria here, it's fairly inclusive. There's quite a few parameters that are provided, but this is the kicker. Where is any discussion surrounding contamination or wear? I mean, that's exactly what we saw on the previous couple of tables. This one only addresses fluid properties, but you know what, that kind of makes sense because the physical and chemical characteristics of the fluid are things the lubricant supplier will know. Now, if they do address contamination, you have to ask yourself the question, is this the limit for any machine or just the limit for the fluid to do its job, generally speaking? And chances are they're looking at it from the fluid's perspective because, of course, they are the supplier. Now, I will be fair, not every limit on that table is garbage. Some of it actually makes some sense. So if it's an outright physical property like viscosity, sure, we can use limits because really it either is or it isn't in grade. If they give us another property like, say, soot, well, that's probably the limit for how much soot can be present in the oil without causing a detrimental effect to its viscosity or some of its additive performance. There's a fuel limit, probably just the viscosity we're worried about depressing. Now, if they do provide any limits on the additives, what you have to wonder is what are they actually looking to accomplish with this limit? And generally speaking, again, most of them are self-serving. So they're wondering about not necessarily, of course, a warranty claim, but just a claim against the performance of their product. So they're really using this to identify their product. So they're not saying if the levels are within the range, the product is working. They're just saying if the levels are within this range, it looks like it is, in fact, our product. Now, when they measure degradation properties like oxidation or acid number, base number, again, what's the threshold that they're giving you here? Is this the worst it can get, and therefore you should change the fluid? How fast should it get there is not covered. I mean, they're not really giving you a lot of information. So again, we've looked at OEM limits, we've looked at lubricant supplier limits. They're not fantastic, that's for sure. Now, you may be fortunate and you may be able to find industry-specific limits. And this is an example of one of the most widely cited tables in the condition monitoring oil analysis circles. If you look across the top, it gives a variety of machine types, so it's pretty inclusive. And down the left-hand column, it shows us a bunch of different properties. Now, you will notice there's a lot of blanks on this table, but for the properties that are filled in, those limits are actually not that bad. They're pretty good. But what most people who see this table or have been given this table don't do is read the title of the standard where it came from. It is an ASTM standard. It's D6224 if you'd like to purchase your own copy. But the title says it's the standard practice for in-service monitoring of lubricating oil for auxiliary power plant equipment. So this isn't just for any gear, any hydraulic application. This is for gear and hydraulic applications inside of power plants, and it's the backup equipment, not necessarily the base-loaded, continuously running equipment. So again, now you have to take all that with a grain of salt and wonder, do these limits still work? Maybe they do, maybe they don't. Give you an even better example and simplify it here. Here's one that exists for the wind turbine industry. This is the Worldwide Wind Turbine Gearbox Viscosity Guidelines. Now, that's a pretty lofty word, worldwide, but we'll take it as it is. And it suggests that the acceptable limit is within 5%, caution is at 8, and alarm is at 10. Now, if you notice, it says it's for an ISO 320 gear oil. Well, ISO has their own limit of 10% to just be considered in grade. So essentially, these limits are a little bit tighter than even the manufacturer limits for the fluid. So it could be possible that you would consider a fluid in caution, but still be brand new fluid, absolutely vetted by the lubricant suppliers. But once it goes outside that, they're saying to alarm it. Well, maybe that makes sense, maybe it doesn't. But the point is, it's worldwide wind turbine gearbox. So this isn't for any other gearbox. It's gearboxes specifically up in the nacelle of a wind turbine connecting the generator to the turbine. That is its own unique characteristics of operating conditions, loads, speeds, etc. Does this necessarily apply to other gearboxes? Again, probably not. So you'll notice that this is yet another example that doesn't address wear and contamination, which are generally among the highest things of concern on an oil analysis report. It doesn't claim that if you stay within these limits, you'll definitely have optimal performance. It probably just means, again, you get through the warranty period without any major issues. The implication is these are end-of-drain samples. It's not necessarily outright stated at any point, but they don't usually go out of their way to say what any mid-interval values might be. They just sit there and say, if this is exceeded, the fluid probably needs to be changed out. So my question is, if you achieve these levels within a normal service, you're probably triggering a lubricant change. But if you achieve these levels on the very first sample, all you're going to end up doing is changing the oil, but not necessarily elevating the alarm, realizing, wow, we got to that level a lot sooner than we should have. Maybe something different is happening. Maybe there's a mechanical issue. But no, we just use it as a guideline for when to change the oil. So these first three examples are not very good. OEM, lubricant supplier, industry-specific ones. Most people, like I said, do rely on the commercial labs. Now, the commercial labs have two different ways they can come up with limits. So I'll go through the first one here, static limits, and then I'll come back to the rate of change is what we call the other ones. Now, the nice thing about static limits and why most commercial laboratories like to use them is you can plug them into your computer and the computer will auto-comment on all the oil analysis results. So this speeds up turnaround time at the lab's end of the business. Now, again, they're implied and they work best on end-of-drain samples, not necessarily all the mid-interval samples. But to be fair, some people will statistically derive their limits, and almost without exception, they use the end-of-drain samples to do so. So they can get downright specific, and they can tailor your limits to a machine type, to a make-model combination. They might even align it with the oil that you're using as well. So they start to sound like they're really good because they're really specific, but does specificity make them better? So let me show you a few examples of some of the issues that I see. Now, when you set a limit, there's a possibility that given changes to the lubricants, the operating conditions, your maintenance practices, anything that might be going on, the alarm ends up being too high. So the problem is it can go into failure mode without tripping an alarm. But just as easily as that could happen, it's possible the alarm might be set too low. And it's constantly in a state of alarm. And we call this cry wolf syndrome because, of course, people just start to ignore it because they're like, wow, that's always an alarm and it still runs. So why do I care? So we have to address the limits in a way that makes sure that this isn't going to happen. So the best thing to do would be to revisit your static limits on a regular basis. And that's why statistical derivation of limits makes sense, right? You can use the last 6 months, 2 years, whatever it might be worth of data to establish your limits. And at least they're a bit more dynamic and they're constantly improving. But here's the issue. When you build your limits, there are a few assumptions that come with that. And the assumption is the sampling location never changes. It's a consistent sump size. The interval as well doesn't change. And of course, nothing's changing regarding how you operate it, what fluid you're using, speeds, loads, temperatures, all these kinds of things. So there's an article that I'm about to show you, not some tables, but they published some tables in this article. And I'm going to show you the statement they made after the tables, because the tables aren't worth reproducing once you read the statement that the author made. But I thought the author said it very, very well, even if it wasn't necessarily the intent of them describing the tables. So hear me out. This is the comment they made after they published 3 different tables for wear metals, contaminants, and additives. It says the warning and limit levels listed in tables 1 through 3 for wear elements, contaminants, and additives are based on, and now they go to qualify where did they get the data. So they said it was on a semi-synthetic motor oil, 1040 viscosity, modern diesel engine, an oil volume approximately 25 to 50 liters using a specific fuel, and with an oil service life of approximately 500 hours or 47,000 miles. So now take all that information and understand what they're saying to you. They're saying that if you try and use those 3 tables that he published and you aren't running semi-synthetic, or you're running a different viscosity, have a different volume, use different fluid, maybe have older diesel engines, maybe it's not even diesel, maybe it's gasoline, and if your operating hours are different from 500 or 47,000 miles, well, this table's no good. So these are great limits, I'm sure, if those are your conditions. So we always have to consider that when labs do this, it is that specific, and if there's any change, then it basically blows the limits out of the water and says it's probably no good anymore. But I thought that's not a very fair statement to say at this point that all limits are terrible. What if one of his limits is actually decent? So I chose one particular limit of his. So I'm going to pull 100 ppm, and this is for iron, as a limit. Now remember, they did say 500 hours of operation. That is one qualifier that we're going to have to stick with. But what I'd like to walk you through now is the issues I have with trying to use even the best established limit of 100 ppm iron at 500 hours of service, and show you how both the sump volume, the sampling interval, and even our own perceptions work against us as to knowing that that value makes any sense or is just no sense. So let me give you the example on sump volume. And there's a poll question coming up here. So if you had a 5-gallon reservoir and there's about 2 fingernail clippings worth of this iron, and you compare this to a 50-gallon reservoir with nearly 3/4 of an ounce of material, the iron, and your third choice now is a 500-gallon reservoir with nearly a ½ pound of iron. These are the considerations we have for the poll question.
Okay, so I've launched the poll question, and again, the question is, which system is experiencing the highest wear? Is it the 5-gallon system, the 50-gallon system, or the 500-gallon system? So y'all can start entering your votes. I'll give it just a few minutes, or I'm sorry, a few seconds actually. So we're up to 45% voted. I'll give you a few more people to weigh in. Okay, so I'm going to close the polling session, and I will share with everyone how everybody voted. So it looks like the 5-gallon system is what was voted as the one that was experiencing the highest wear. So Evan, do you want to continue on with that?
Sure. And here's the issue. Which one is experiencing the most wear is not going to be seen on an oil analysis report, because all 3 of those would measure out at exactly 100 parts per million. And this is the issue we have when we start changing sump sizes, but we try and use the same limit that was built on a particular sump size and doesn't match what we're currently operating. So you can appreciate that in the 500-gallon reservoir that required nearly a ½ pound of material, that might have been an entire gear tooth out of a gearbox. But in that 5-gallon reservoir, like I said, it would amount to only about 2 fingernail clippings worth of material. Very different physical amount of iron, but in the end, because we measure concentration, all 3 of those examples measure out exactly the same. So when we try and use limits, it doesn't really work. And I think it's best illustrated by showing you this blue line here, which is the curve that represents where the 100 ppm limit came from. But the black line I have added to show you what if it is wearing not at the same rate, but 50% faster, 50% more wear debris is being created, but the sump size has doubled? And what you notice is that the black line does not intersect the threshold where the first alarm would go off. So in fact, that system's wearing worse, but because we have the static limit of 100, we have not tripped the alarm. And we don't know that that's occurring. And that's just because the sump size would have been built off something like, say, 30 gallons, and we're comparing it to a 60-gallon sump. So we always need to consider what's going into this calculation and how much that affects the ultimate outcome of the limited usage we have for a limit. Now, I'll give you a few more examples here. So assuming then the 500-hour drain interval that was stated in the article and 100 ppm for iron, let's wonder what would it look like if we extended the drain interval up to 750 hours. Well, 750 hours, that's 50% longer, so you might expect 50% more wear. So 150 ppm should be considered normal. But my point is, because we just set this one alarm at 100, 110 ppm would actually trigger the alarm. So even though you've run 50% longer and experienced only 10% more wear, an alarm goes off because the alarm is static. It doesn't move with the data. So you can see how you're going to end up possibly in that cry wolf syndrome again. So this is what I refer to as the eventuality factor. If you set any limit, eventually the oil will cross that threshold. The question isn't whether it crosses the threshold. The question is, how soon does it do it? Does it do it within the normal expected interval, or does it do it faster? Because if it does it faster, I need to know and I want to take greater action. But if it does do it within the normal interval, then that's considered normal. And if it takes longer than the normal interval to do it, well, obviously that's an improvement perhaps, or maybe something else is going on. So we have to be cautious when we apply these static alarm limits to know that eventually we're going to cross them. Doesn't mean there's a problem. It just means perhaps we've extended the drain interval or the rebuild time or whatever it is, being long enough, we're going to come to that set of circumstances that raises the value. Now, the other thing I'll point out is that when we set these alarm limits, what we end up doing is missing overall trends. In this data here, you can see that the data is increasing. It goes into alarm. Obviously, corrective action is made. It goes out of alarm. And it goes into alarm. Corrective action is made. It goes out of alarm. And all we notice is this pattern of in and out of alarm. We don't necessarily notice that it's constantly increasing. Now, maybe that's increasing for a bad reason. Maybe that's increasing for a known reason. But we've missed the overall trends because we're just so concentrated on if it's an alarm and how do we clear the alarm. So one of the things I stated with the implied data from the lubricant suppliers, the OEM, was that they're always based on end-of-drain samples. So then some people think they start getting clever and they go, well, what if we just include more data? If end-of-drain is not necessarily the best piece of data or the only piece of data to use, what if we just include more data? Won't that make it better? And funnily enough, the more data you include is not your end-of-drain data, the worse it gets. So if you start including your mid-interval samples data and try and calculate your alarm from this, what you're going to do is you're going to approach the halfway point. So I'll show you what I mean by this. So we're assuming that at end of drain, 100 ppm iron is what's going to be achieved. So if we take one piece of data, one end of drain sample, and calculate the average, it's 100, of course. But what if it takes two samples to get to the end of drain? Well, obviously one sample is at the halfway point and one sample is at end of drain. The sample at the halfway point has a value of 50 ppm, and of course the same sample at the end of drain has 100. Well, our average becomes 75. If we split it into three and have one at the third of the way through, one at 2/3 of the way through, and still keep the end of drain data point at 100, what you end up is drawing the average down to 66. And just to show you where I'm going with this, I added in twice as many data points again, and you can see how the average gets pulled down even closer. So my point is, with an infinite amount of data, you would actually arrive at an alarm limit of 50 ppm, assuming that you're achieving 100 ppm at end of drain regardless. So the more data you add, the worse it gets. Therefore, logically, you can only use the end of drain sample to calculate your limits. But that limit works very, very poorly on all the samples leading up to that end of drain. Okay? So if we assume 500 ppm is what's achieved, or sorry, 100 ppm is what's achieved in 500 hours, then we would think 50 ppm in 250 hours is normal. But the problem is that with an alarm limit of 100, we don't trigger the alarm if we get to 90 ppm in 250 hours, because it's still below 100. And even if it happens to cross over 100, we don't elevate the alarm and say, wow, you guys got to this limit in half the time you normally do. An alarm just gets set off. It's just a blinking light. The same alarm goes off regardless of when it goes off, how quickly or how slowly. So it's very difficult then to establish a static limit for mid-interval samples. Even if you know it's always, always, always taken at that same interval, even if you could lock that down, which most people can't, even if you could, you're not going to establish a logical limit. So just to show you this, again, the blue line is exactly the same blue line I showed you before that established the 100 ppm in 500 hours. What I'm showing with the black line this time is I've doubled the rate of wear. So they both start at the same point, but the black line's increasing at twice the rate. And all you notice is that it crosses the alarms 1 or 2 samples earlier. Again, we don't know that it's worse. Unless we're counting how many samples between alarms, all we know is it crossed an alarm threshold and the light goes off and it tells us, take action. So now let me provide you with another example so we can have a poll question here. I'm going to show you a 2 ppm change. Now, a 2 ppm change, if it goes from 1 ppm to 3 ppm, looks like a 200% increase. But if it goes from 11 to 13 ppm, that only looks like an 18% increase. And if it happens to go from 101 to 103 ppm, it's only a 2% increase.
Okay, so here's our next poll question. Which system has undergone the greatest increase in wear? Is it 1 to 3 ppm increase? Is it 11 to 13 ppm increase? Or is it 101 to 103 ppm increase? So go ahead and cast your vote. I kind of have the feeling Evan's trying to trick us again. Looks like we're up to about 50% voted, so I'll leave it open for a few more seconds. Okay, we're up to almost 75%. Go ahead and cast your vote. Nobody knows what you answered. Take your best guess if you're not sure. Okay, we're up to 75, so I'm going to go ahead and close it out. I'm going to share the results with you. And so, Evan, are you surprised by this? It looks like more than half chose 1 parts per million increasing to 3.
Yeah, and
tell us what the answer is.
It's funny because during voting it was the other way around. Most people were choosing the last answer, not the first answer. So I'm glad to see people were picking an extreme and avoided the middle one. But this is the thing. The question was which one was experiencing the greatest increase, right? Not which one has the most wear material. So whether it's 101 or 1, the increase went up by 2 parts per million. And now, saying that they're all the same sump size, that actually took the same physical amount of iron, or whatever we're measuring wear contamination here, to cause this increase. 2 parts per million is 2 parts per million. It doesn't matter what the starting value was to what the end value was. The difference in all of these was exactly 2 parts per million. So we have this sort of conflicting decision, because when 1 goes to 3, we go, that went up by 200%. It tripled. It's gone up exponentially. It's horrible. But if we see a result go from 101 to 103, a lot of people just dismiss it and say, well, that's practically the same result. The point is, 2 parts per million in an oil sample is the same 2 parts per million regardless of the concentration that the changes occurred at. It's the same amount of material. So we are often fooled by this, and what I think it comes down to is that We just don't have a solid understanding of what 1 part per million is. We think that 1 part per million is insignificant when values are low, and we think 1 part per million may be more significant when values are high, or vice versa. And the best way I can think to explain it to somebody is just simply imagine that there's a dollar, $1 sitting there. Now, if on one side of the table the dollar sitting on, you've got a millionaire with $1 million, and on the other side of the table, you've got somebody who's got no money, they're broke. You think, which one on either side of the table wants the dollar more? Now, barring any psychological reasons for this, obviously you're looking at it just from the perspective of somebody who's got $1 million looks at that $1 as nothing. They go, well, I've got $1 million, I don't need the $1. But the person on the other side of the table who's broke sits there and says, wow, I don't have anything. That dollar, that's something. That'll, buy me a coffee perhaps. Certainly not a Starbucks coffee, but somewhere else. The point is, the dollar on the table is the same dollar. It doesn't matter. A dollar is a dollar. A ppm is a ppm. Right? This 2 ppm that I'm showing you here is the same 2 ppm in all three examples. It's the same amount of an increase, the same amount of material creating an increase. But we just tend to view it from these skewed perceptions of what's it look like as a percentage. And just to give you a quick visual on that, I'm showing you some data that's shifting around by 1 or 2 parts per million. And you look at this data and you think, wow, it's really taking off at the end there. I'm worried what the next sample might look like. And if all I do is change the scale on the graph, this is what the data looks like. And it's much flatter, and you probably aren't in near as concerning mode as to what's going to happen next. And that's just the issue that we have with this, what I call perceived value versus the actual physical amount, which truly what has changed in the lubricant. So we always need to readjust basically our compass on this and say, where am I going with this information? Do I truly understand it, and am I following the right path, or am I off? So what a lot of people try and do then is ignore the overall picture. And they sit there and look at this and say, really, what it's going to boil down to isn't whether or not I cross a line in the sand, a static limit. It's, like I said, how fast do I get there? So where people think they start to really improve their system is by going to rate of change. Rate of change is also known as time-dependent limits. Now, this does absolutely require the reporting of hours then. We need to know how many hours or days or some tangible time value on the samples. Maybe it's not 100% accurate, but we need something to gauge. Has this sample got as many hours on it as the last sample, as the previous, so on and so forth? Now, in this case, when you start doing rate of change, it actually improves when you have those mid-interval samples. The more of them you have, the better your data becomes. Now, to be fair, it will be skewed by top-ups if there are any significant volume. But the worst thing working against rate of change are the built-in assumptions. And one of the most commonly misconceived ideas when it comes to the assumptions that we're making with rate of change is that the rate increases over time. It's the snowball effect, right? The worse it gets, the faster it gets worse. But the other assumption we have working against us is simply that the values reset to near zero or new oil values every time we change the oil. And that's simply not true. So let me show you a bit of a noisy graph here, and I'll explain what we're looking at. So this blue line, the jagged one that goes up and down a whole bunch here, this is, as you can read off the left-hand axis, the average parts per million per 100 hours. So here's the scale for the parts per million per 100 hours, and then down here's the hours on the oil. So this shows us with increasing hours, we have increasing wear. That kind of makes sense, and that's intuitive. The red line, though, is the number of samples, as you can read off the right-hand axis here, the number of samples that created this data point. So right here, this data point has nearly 750 samples supporting that piece of data. So that means I'm probably pretty confident in these values. So what does this piece of data tell me? It tells me there's approximately 12 parts per million per hour iron generated in this particular Caterpillar 3406 engine. Now, the other peak that you might notice on the red line is way over here. It's not a very big peak, but it's something. And it happens to be at 500 hours. Well, that kind of makes sense. Apparently, there's a lot of samples taken at 250 hours. maybe that's the sampling interval. So 250 hours later at 500 samples, or 500 hours, there's a sample taken. Well, logically, if we can achieve 12 parts per million after 250 hours, what might we achieve at 500? And the logic would be 24 then, right? You double it. But survey says it's about 21. It's not exactly double. So how does that make sense? Well, how we can make sense of that is by looking at the last couple of lines on the graph. Now, this green line here, this is taking the blue line that you see, the jagged blue line, and dividing it by these hours so that we're reporting now in parts per million per hour. And of course, it's going to be very high at a near zero value because of very few hours. It doesn't take much to make it high. But the line eventually somewhere around here starts to settle out. And what do you notice about the green line? If anything, it has a slight downward trend. So the rate of where it doesn't increase, the rate of where it doesn't even remain the same, the rate of where it apparently is decreasing. Now, astute observers might notice that on the blue line here at hour zero, it doesn't begin with 0 parts per million iron. There's inherently 7 parts per million already there. So the question is, where did it come from? Why is there 7 parts per million in my oil right from new? And the answer to that question is simply put this way. When you change oil in any type of system, it doesn't have to be an engine like this particular example, but any type of system, you're never going to get all the oil out. And when you can't get all the oil out, we refer to the remaining oil as oil hang-up. Oil that's hung up in the system through piping, galleys, whatever it might be. It's oil that doesn't readily exit the machine. Now, statistically, most of us use numbers of upwards of 25% of the oil. And those of you who perform your own oil change in your own vehicle probably know this, right? You put about 4 or 5 quarts into your vehicle if you drive a gasoline engine. And when you take the oil out at end of drain, you only get 3.5. There's at least a quart you never get back out. And some of us attribute this, of course, to losses, but the point is that there's going to be some of it hung up in the system. Now ask yourself this, that remaining oil that is hung up in the system, does it look the same? Is it better? Or is it worse than all the other oil you took out in terms of the amount of wear material and oxidative insolubles and all kinds of nasty stuff? And you're probably thinking, yeah, it is the nastiest, gummiest, sludgiest oil that's remaining. Well, funnily enough, even though 25% by volume might be remaining, what we've noticed when you do these kind of linear regression studies is that about 30 to 40% of the value at drain will be present in the oil when new. So going back to our value up here of 21 parts per million, what would 30 to 40% of that value be at hour zero? Well, it turns out 7 ppm is not too far off. So when we consider that we're always starting with 7 parts per million, ultimately that should be our baseline, not 0, 7. So what if we simply subtract 7 from all these values? And if we subtract 7 from all these values and then divide that result by the number of hours down here on the oil samples, you get the purple line. The purple line is a corrected rate of change. And that corrected rate of change is supposedly the intelligent way of establishing an alarm limit. Well, again, all I'll point out is, what do you notice about the purple line? What's the trend? The trend is flat, and again, if anything, it actually slightly decreases over time. So for those of us trying to use rate of change and expecting the rate to change, by the time the rate changes, it's probably too late. We've probably alarmed it as more of a lagging indicator than a leading indicator. So it's not a great way of doing things. The rate of change seems good in theory, but it doesn't really work. So I've shown you that OEM, lube supplier, industry-specific limits, and even 2 different ways that the labs could do the limits on the oil samples, all have flaws, all are working in a very limited range where they could be good. And for most of us, they're just less than optimal. So there's got to be a better answer to all of this. And there is. That's the point of the discussion here, is trending. So having spent all that time picking apart how everything else doesn't work, let me show you what does work. And a tool as simple as linear regression, right? This is not complicated math, can establish a trend and identify when the data is going outside of trend. it needs as few as 3 samples can establish a trend, and the 4th one can now be considered in or out of that trend. If there's any significant deviation from what the anticipated trend is, then we can identify it. And that doesn't matter if it's going up, if it's going down, or if it's flat. As long as it follows trend, it stays out of alarm. And for those of you who still want to use limits or still set on limits, or some of us might be held by regulatory limits, it works in harmony with those. You don't have to give up the limits to use the trend. The benefits of trending, though, you'll see. I'm going to walk us through every example I already showed you and then throw a couple more out there. But what happens if we don't revisit our calculated alarm limits and the alarm limit's too high? Well, I've used some sort of blue fuzziness here to the lines to identify one standard deviation. And you can see that trending software has identified that current piece of data as outside of trend. So it would alarm it. It would tell us something's gone wrong, even though we haven't crossed a threshold. On the flip side, when we have that cry-wolf syndrome, this now rewards the consistency and says, no, there's no reason to alarm this. It is constantly within the same range. Leave it alone. Turn off the alarm. Right? So this actually helps us get rid of nuisance alarm. That eventuality factor I spoke of, it now looks at it and says, no, that's the projected trend. I expect you to increase slowly over time. So as long as you keep doing the same amount of increase for the same amount of time, I am not going to alarm it, regardless of how high you eventually get. And that really noisy data I showed, again, it just sits there and says, look, it's following the overall trend. So it won't keep going alarm and out of alarm or whatever it's doing. It again rewards the consistency and says, yeah, it's fine. So even if you're doing frequent fluid changes or turning on and off filtration or any other operational decisions like that, the trending software can account for it and not worry about it too much and say, no, it's still following the trend, leave the alarms off. And really, if you come down to it, one of the most common complaints of anybody who uses oil analysis and pays close attention to their alarms is they have too many alarms, right? Most people don't sit there and complain that stuff is missed. Most people complain that they don't know what to do with all the alarms.
Okay, so we have our last poll question. What kind of maintenance strategy does oil analysis fall under? Is it reactive, preventative, predictive, or proactive? We'll give you a few seconds to vote. We're about up to 75% voted. Give you a few more seconds. Everyone seems pretty confident of this answer. So let's see if Evan is tricking us again. So I'm going to go ahead and close the poll. We are at 83%. And here's how everyone voted. It looks like a large majority chose predictive maintenance. So Evan, go ahead and let us know if they're right.
So yeah, the most common answer people pick is predictive, because when you think of predictive maintenance as a strategy, it usually employs condition monitoring, and one of the tools of condition monitoring is obviously oil analysis. But my point is this: the way most people tend to use oil analysis is not actually in a predictive manner. What they use it like is a reactive manner. And to illustrate this point, think of it this way. When do you take action? If you're doing oil analysis, when do you take action? Do you take action when the trend indicates that it's going out of trend and there's a potential for a problem, or do you wait for the alarms to go off? And most people tend to wait for the alarms to go off. Now, to be fair, some people are assuming that the alarm is set in such a way that it is an early enough warning in terms of the trend. But as what I've already shown you, hopefully explained, that's not always the case. So when we wait for oil analysis to trigger an alarm, generally the way most people use oil analysis, it's equivalent to using your smoke detector to tell you when your muffins are done baking. Right? It comes when the failure is already happening. So it's a bit too late. It's a lagging indicator, and more or less, oil analysis is actually being used as a reactive tool because we just react to it. We do nothing with it until the alarm goes off. So in that sense, if you're following what I'm saying here, we really kind of use oil analysis more like a reactive tool than we do as a predictive tool. Now, it's intended to be a predictive tool. I will grant you that. But most of us don't seem to use it that way. And here's a great example illustrating that. Look at the overall trend here. Right? If you just look at the actual line and look at the data, it starts at 8 ppm, drops to 4, goes back up to 7, drops to 4, goes back up to 6, drops to 1, climbs to 3, and then goes to 7. If you saw that string of data written out and you saw that the latest sample was 7 parts per million, you probably wouldn't alarm it. Because human nature would be to look at this and go, well, it was 8 in the past, it's only 7 now. Well, why should I alarm it? The point is that maybe 7 isn't necessarily too high at the moment, but the trend has been slightly decreasing, and the latest results went 1, 3, 7. So where do you think the next one's going to be? If it continues this trend, the next result is going to be at least 11, if not higher. And the next one would be outside of those pre-established static limits you see on the graph. So my point is, this is what would actually make oil analysis work in a predictive manner rather than just in a reactive manner. Because as humans, we would look at that and just interpret that the data itself as normal. We'd say it's a little noisy, but we wouldn't alarm it. But when the next sample came in at 11, it would trigger an alarm, and then we would do something about it. But what I'm saying is, I think we're being reactive at that point because now it's gone into failure mode. At this moment in time, on this particular example, we're in predictive mode. And that's really what we want oil analysis to be. Another good example of that is just to flip the data around a little bit here, and you can see the results went from 7, they did alarm at 11, but then they've come back down, and they've been hovering in the 6 to 8 range, but the latest result is only 2. Now again, for a lot of people, if they saw that data written out, they'd look at the 2 and they'd say, I'm not going to worry about it. It's as low as it's ever been. It's in fact better than normal. This is fantastic. But with trending, you would establish that as being abnormal. And you'd have to ask yourself why. Now, for those of you who are familiar with oil analysis, and say we're talking about iron content still, iron, the way it's measuring only small particles, typically in the 0 to 5 micron range. Around 5 to 10 microns, the accuracy really takes a nosedive. And any particle larger than 10 microns is essentially not counted accurately at all. So for the iron to have decreased down to 2 parts per million suggests that perhaps the iron particles have gotten so large they're falling outside the scope of analysis. So it could be that this has gotten significantly worse. But again, we tend to look at data as strictly data. So we just look at the numbers and say, what's below threshold, and we move on. But what this data is telling us at this moment is it's outside the normal trend. Something different is happening. So we should look into this. We should investigate further. I'm not saying we change the oil or do anything with the machine, but we should at least figure out why we think the value has trended in the opposite direction that we would normally expect and has deviated so significantly. So the whole point of trending is simply this. Trending is actually predicting the future values. It's anticipating that the alarm is going to go off, not just waiting for the alarm to go off. So it doesn't use the eventuality factor against itself. It contributes to it. It says, yes, following this trend, we will go into alarm. Based on a deviation or based on a path that is taken, trending works that way. So when we trend results, it's part of the interpretation. Right? We are considering other factors, but what I'm saying is it should be the most substantial part. And the nice thing about trending is it can work on a one-off as well as a large fleet. It does not require people to fill in all that make, model, or some size information. And all the things I was stressing, work for and against us now aren't even considerations. Trending works on the mid-interval samples and the end-of-drain samples, so you don't need to worry about when the sample is being taken. At any point in its life, the trend is what the trend is. And just to make sure we address this one more time, it still works in conjunction with any limits if you want it to, or you can ignore limits and have it work independently. It's up to you how you'd like this all to work. But getting to that last poll question, trending does become predictive. It keeps oil analysis as a predictive tool, not a reactive tool. And that is really the crux of the whole discussion, because like I said, so many people just, if they get a normal report, file it away without even looking at it, not trying to see if there's any potential trend to identify, that the next report they're going to get may have a problem, they just file it away and say, well, there was no problem today, and they carry on. But if they have one that's an alarm, they suddenly react. And again, like I said earlier, sometimes we get so many alarms, we start to use the cry wolf theory, and we start ignoring alarms, and then now we just took one of our best tools and turned it against ourselves. So I hope this webinar has been informative, and I think that if you consider switching away from limits and trying to rely on trending, what I'm saying is that with trending, your possibilities are limitless. So with that, I'll turn it over to Carrie for questions. If you don't want to use the question toolbar at this moment and just would rather email me at your own convenience later, I've got my email address up on screen. But for now, I'll turn it over to Carrie and see what we've got.
Yep, and I'll include your email in the follow-up email that I send to everyone. I'll include your email address on there. So we do have a couple questions. We've reached our 1 hour limit, but I think it's worth it to go ahead and ask these questions. If you need to go ahead, but they'll be on the recording as well. So the first one is, Evan, what happens if you get one really bad result from a bad sample? Does that throw off the trend?
Well, the nice thing is, yeah, with trending, it doesn't. It's not like a bump in the road pushes the threshold way high or way low, whichever direction it's going. The trending is always looking at the past bunch of samples. So when you start using statistical analysis on it, having one bad result out of 3, yeah, it has a bit of a skew to it. But as soon as it's one bad result out of 4, that influence just diminishes. So if you ever get a really bad piece of data from a bad sample, it doesn't completely reset everything. It does have some influence, but the influence is minimized as you carry forward. It recognizes that, no, that was an anomalous piece of data, and it doesn't necessarily include it anymore. So the kind of fluctuations we get when we do oil changes and those kinds of things, they're accounted for as well. So no, trending, it's good that way. It's nice that it doesn't get fooled easily, I guess is the way to put it.
Okay, and here's another one kind of in the same mind frame. What happens to the trend when the oil is changed? Is it reset each time?
Yeah, it's not really reset, but it is factored in. So essentially what you kind of expect with, very few samples in between drain intervals, more or less a sawtooth pattern emerges to the data, whether it's going up or going down. And that just widens the band of what the trend is expecting as an overall trend, but in the narrow results between each oil drain interval, you're expecting a fairly continuous slope. So you're kind of measuring the slope of each tooth, but you're looking at the overall roughness of the saw at the same time. So again, trending can account for all that and still find the anomalies, the deviations from trend.
Okay, I have someone who's asked several questions. We might have to save your questions for offline. Here's another one. What is the measuring error in an FTIR scan?
According to ASTM, which has 4 different ASTM methods for 4 different FTIR parameters, the reproducibility error 19 times out of 20 is less than 1 unit of measurement. And units of measurement are absorbance per centimeter. So whatever the value is, it's not going to deviate by even 1 unit of measurement. So if you're getting 6 and it changes to 7, that's a real change, because we don't tend to report decimal places on FTIR data. But 1 unit of measurement is expected. Maximum error, allowable error.
Okay, I'm going to do one more question. Like I said, there are a couple people on here that have multiple questions, and we're going to have to save those for offline. Evan can email you. The last one is, do all labs do this kind of trending?
No, actually, many labs rely on the static limits. There are a couple out there that I'm aware of that at least give you the option of rate of change, and that works for some customers better than it would work for others. Kind of depends on how many mid-interval samples you're expecting. But by and large, no. The industry has focused on for years, and again, going back 60 years to its inception, of using previous data to establish a particular threshold limit and sticking with it. So very few labs out there are like us that do some kind of trending in conjunction with the overall analysis. So, yeah, you have to ask to find out.
Okay, so I'm going to go ahead and close us out for the day. We did go over our, actually usually 45 minutes, but this was a great webinar, Evan. Thank you so much. I love your stories. Your analogies really help me understand everything, and I think our attendees will agree. So everyone have a great day. Watch for the email I'm going to send with the survey, as well as a separate email will come with the recording. And that's it. Thank you for attending. Thanks, Evan.
Thank you.